now we go into the topic, and it's surface energy balance, and this is related to the previous slides because we talk about the air side properties. We don't talk about the surface, but whatever there is in the air comes from the surface. The heat, the moisture, and so on comes from the surface. So we also need to know about the surface itself that releases the heat, releases the gases or other things from it. So I'm going to read through. The surface energy balance determines the amount of energy flux available to evaporate surface water and raise or lower the temperature of the surface. Right? So whatever it is there is in the air, it comes from the surface. Whatever water there is in the air comes from the surface. Ultimately means that maybe some of them accumulates in the air before, but then long time ago it comes from the surface. So we need to know how much there is in the surface so that we can also understand what goes on in the process of transporting it out of the surface, as well as what goes on in the atmosphere, because we know the total amount, and we know how much is in the air, then we can find some relationship between the two. This is the source of all these parameters in the air. Now, the energy budget at the surface requires consideration of fluxes of energy by conduction and by convection, of heat and moisture through fluid motion, as well as radiation. Means from the sun. The local surface energy budget depends on the insolation, or the sun, solar radiation, the surface characteristics such as how wet it is, how much vegetation there is on the surface, and this relates to how wet it is also, because vegetation releases water vapor. Albedo, you already want to know what this is, the reflectance of the surface, and on the characteristics of the overlying atmosphere. That means the parameters in the air, because if the parameters are quite close to the surface parameters, then the gradient is small. When the gradient is small, there's less flux. But if the air is dry, for example, and the ground is wet, then the gradient is large. That's how the overlying atmosphere affects the surface itself. So this is the surface energy balance equation. Don't worry about the word equation there. It's just in the end, the sum on the left should equal the sum on the right. That's all. Like say 100 equals to 100. So here it says the net radiation is equals to, I think this is sensible heat, H. This is latent heat, and this is storage. So sometimes they use different symbols for this. That's why I was a bit confused with that one, because I use mostly Rn equals to H plus Le plus G. Right? So sometimes you see Le instead of HL. HL stands for latent heat. Le is also latent heat. G is storage. Hg there is storage. Storage within the surface. So this equation says that the only source of energy comes from the sun. So when the sun gives energy to the surface then distributes it to other components. So let's say 100% comes from the sun, and this 100% is distributed in the form of sensible heat, evaporation or latent heat, and also some of it is being stored. So you can imagine like 100 coming in, then it becomes like this is 10, this is 50, then this is 40. But in the end, when you total them up, you get 100. Just it's being partitioned, or it's being separated into the different components. So this is in diagram form. You have Rn coming in. This latent heat, evaporation, right? So it evaporates. So whatever energy that comes from the sun gets released back into the atmosphere through this evaporation. And there's also some sensible heat being released into the atmosphere. This is dry heat. This is wet heat in the more common terms or understandable terms. And then there's also some energy being stored by the land or by the surface itself. This one implies that the sensible heat is much larger than the latent heat, but this really depends on the location. Can you guess, in tropical locations, which one is larger, this one or this one? Latent heat larger or sensible heat larger? Tropical. We have a lot of vegetation. Latent heat. So latent heat is larger than the sensible heat in tropical regions, over water surfaces. But over deserts, then sensible heat is a lot larger than, because there's no water source from the desert surface. Same goes for very dry urban areas, like say even in towns. But then even towns, we have a lot of trees in between the buildings that also gives off some latent heat. Sign convention. means it's just to set some rules on what we mean by positive, what we mean by negative. Because some people could say positive is upwards, negative downwards. Some people could say the other way around. So here it says if it's positive when downward. So if it's going downwards, then we call it positive because we think that the sun, energy from the sun is coming into the system, so it adds to the system. And then if it gets released like this, then it becomes negative, right? So positive when downward, radiation. Others positive when directed away from the surface. Okay, radiative heating of the surface means the net input of radiative energy to the surface is the sum of the net short wave and net long wave flux density at the surface. Short wave comes from the sun. Remember, anything less than 4 micrometer is from the sun. Anything more than 4 micrometer is considered long wave. It's from other surfaces than the sun. So this net radiation, the one here, is the net input. So we have some, okay, the large component is this one. This is very large. This is the energy that comes from the sun coming in. But then there's also some that gets reflected back, shortwave radiation. So we need to minus this. And then the surface that accepts the shortwave would also emit some energy, but it's in a long wave portion. So this one could also be large. But then it also accepts some long wave that comes from other objects. For example, here emits, but this also emits, and it goes in, so on. So it's all about in minus out, in minus out. So this net plus or minus this net, you get the net radiation, the total radiation or energy. So just to be formal here, it says S downwards, incoming shortwave radiation. S upwards is reflected shortwave radiation. Then L downwards, incoming long-wave radiation. L upwards, outgoing long-wave radiation. Okay. Absorption of solar radiation at the surface. We have this coming in and going out, but we can summarize this to become coming in, and then parenthesis 1 minus alpha or albedo reflectance. So these are some values for albedo in percentage, and if you already work with albedo values in your air quality modeling project, this is more than 1 because it uses percentage, but it's only between 0 and 100. So fresh snow, 75 to 95 because it's white, so it reflects a lot of it out. So you've noticed if we put here 0.95, that means, so 1 minus 0.95, we get 0.05. So 0.05 times whatever incoming that comes in, that means a lot of it gets reflected back out. Let's look at water. We're covered by a lot of water around here in Malaysia, so that's about 10% or 0.1. But it changes quite a lot. You see there's a star there, means it's an average. So it can actually vary quite large, means that it could absorb or it could reflect quite a lot as well. And then you've also seen this equation before, haven't you? The Stephen-Boltzmann equation. Basically, this equation is, what is L there? The long wave radiation, the energy, is equals to a constant times temperature to the power 4. The Stephen-Boltzmann equation. So the net long wave radiation, this is net, is equals to the constant, this one, times epsilon, the emissivity. So that's also a constant of the sky. The temperature of the sky is power 4 minus the emissivity of the surface times the temperature of the surface power 4. So here we say that the sky is the incoming long wave radiation, but then the one that reflects is coming from the surface, because there's also some long wave that comes from the clouds, from the air molecules, and so on. That's why we have to take into two accounts. So the net is from the sky minus the surface. Now the long wave emissivities of most natural surfaces are between 90 and 98%. So this is this constant values. Depends on the type of surface. So this is a typical energy balance profile, or the changes of energy throughout the day, from 12 o'clock at night until 12 in the afternoon, back into 12 o'clock at night. So let's go through this first. Maybe I left something out, then I'll talk about this. So it says sketch of contribution of radiative fluxes at the Earth's surface toward the net flux F star during a daily cycle under clear skies. That means we can think of no clouds, because the clouds also have some reflectance in them. And positive values represent inputs toward the surface, negative are fluxes away. So probably you've seen this already. This is something like the bulk transfer equation. So arises from the vertical temperature and wind speed differences in the surface. Okay, this is sensible heat flux, Cp, and then that is a sensible flux, sensible heat flux from eddy covariance, and we can, when we multiply with the constant, then we get this H. Now during daytime, the sensible heat, the dry heat that gets released from the surface, a net radiation surplus exists. That means radiative heating. That means the surface is being heated. The surface usually loses turbulent sensible to the atmosphere. During the day, sensible heat will be released from the surface. At night, net radiation deficit exists. That means radiative cooling. So the surface gains turbulent sensible heat from the atmosphere. So basically, common situation is where during the day, then heat will be released from the surface, and night heat will be absorbed by the surface. And we call that radiative heating and radiative cooling. So less common case is where the surface can receive turbulent sensible heat energy during the day, such as when warm air advection over cold surface. The same goes for latent heat. This is similar to the bulk transfer relation, but this one uses this term instead of the U delta Q. So it arises from wind and humidity difference between the air and the surface. It is associated with phase changes of water. Phase change means evaporation, means from liquid to gas. By the way, this LV constant here is 2.5 times 10 to the power of 6 joule per kg, so that's a common constant to use. This is the amount of energy needed to evaporate per kg of water. Now, when there is evaporation, there's no change in temperature. There's change in phase. Then there's the Bowen ratio. We talked about this before too, so it should be easier for you to understand here. So typical value for desert says 0.1 to 10. I think maybe you can guess. It's a ratio between sensible heat and latent heat, or LE. So if it's a desert, it means that LE is very small, right? And when this is very small, then the Bowen ratio should be very large. So it should be 0.1 or 10. Over the desert, it should be about 10. Now, if the turbulent fluxes are not known, but there is some idea of how dry a surface is, the surface energy balance may be closed. What I mean by closed here is, remember this Rn equals to H, oh there it is. When I say closed, 100 is equals to 100. This is closed. But then, you know, when you have different measurements, definitely it's not going to be the same, because you use this one, different sensor. This one you use different sensor. So it's like very rare where you get exactly the same. That means it's perfect measurements. So most of the time, I'll get like say 100 here, and this is about 70 or maybe 60. Over water surfaces, it's actually 120. It's not closed. There's something here. Doesn't mean that it's 100 equal to 20. It just means there's something that not accounted for. It's not closed. So if this is like this, if it's 100 to 70, 60, there's something that is not accounted for. And when this happens, means that the energy balance is not closed. So sometimes you see that in papers, right? Where they talk about the closure of balance and so on. Now we talk about the ground. Now this is something that I don't have much experience with because I study water surfaces. But let's just go through this because some of you might be working with soil, right? And how do you quantify soil measurements? How do you quantify parameters from the soil? Or at least that you be aware of other things that you can do to measure the soil. This is the last component of that energy balance. Remember, it was Rn equals to H plus Le. So we talked about H and Le. Then there's the G there. So if remember this part here, and then I said that this now was 100 and here 20. So why is it 20? Because I measure this using EC, but then I didn't measure the storage. So my guess is that this part is a storage, which is understandable because water can absorb a lot of heat, right? But for me to measure this, I need to have multiple level temperature sensors. This one brings us to discussion of the ground heat flux. So ground could be underwater, it could also be soil. So same concept, if you want to get the heat storage in the ground, you need to have multiple level measurements in the ground as well. But it doesn't have to be that deep. So heat conduction into the subsurface or below the surface, it follows this equation. Basically, it means the temperature difference divided by height. So different levels, you minus the temperature, then you get the height, multiply with a constant, and you get the ground flux. So K is the thermal conductivity or thermal diffusivity times heat capacity. This is a constant. The different soils or different surfaces would have different K values. That's where you need to go and do the measurements there. So K, this one is from the data there, but this K is a property of the soil or the surface. This K would change based on density, the porosity, the liquid water content, etc. So I guess here, this book in page 50 gives us a value of the CP, K, and so on to first estimate the K if you don't have the data for it. Diurnal cycles and annual cycles define an active layer. So the heat flux coming from the ground or the capacity of the ground to absorb heat changes throughout the day because of the sun. It also changes throughout the year because of the season. Although we can more or less estimate in Malaysia that the annual cycles will be fairly constant because we only have one season, right? But sometimes it changes depending on how wet the ground is. If it's raining a lot, then it could be more wet. So that could change also because depending on the year, depending on rain. But then we don't have a defined rain pattern anywhere. It's like sometimes it rains a lot and it doesn't rain and rains a lot again. So in the end, if you average it out, then it's going to be the same. So again, these are the you see this just now. This is the same. This is the same equation as just now. Notice that this is temperature with height, and this is both concerning heat. This one is temperature with time. The changes of temperature with time should be equal to changes of heat with height. It's called thermal energy conservation. Okay, this one, actually you want to use this one, means that you have to have multiple level measurements of temperature. How about this one? You just have one level. Does it make it simple? So that means if you have one temperature sensor here, but you need to record with time. Then you multiply with rho Cp, then you should get the same changes of heat flux with height. This equation, this part here is from here. So del T over del T is equals to this one. That means this one is a double integration, double differentiation of this. What it wants to highlight is this K here. Once you do this, you have this K, and this K is this thermal diffusivity. And this, it's not exactly K, it's called kappa. Kappa is a Greek letter for this K here. This is K, this is kappa, equals to K over rho C. That's thermal diffusivity. But yeah, it's just, okay, you can break this up into here, and you can get this and so on. And then there's this equation here. Now this equation is an approximation of how temperature change in the ground. T naught, that means that T at temperature at time 0 equals to the average temperature plus a constant A cosine the period omega T. Let's say you don't have temperature measurements of the ground. Can you approximate it? You can approximate it using that equation. So you can imagine the temperature variation change according to the cost. So it's just a matter of fitting this into temperature. So that's just one way to approximate this variation. And then they make further refinements with height and temperature and time. So here is for one level, while this one is for multiple levels. So you can use this one actually to approximate the temperature of the soil without actually having a thermistor or a thermometer or a temperature sensor. Let's see what it looks like. So you saw the complicated equation and all that. If you plot it out, it looks something like this. This equation here. So this one highlights a few things. But again, I said that I don't deal with soil as much, but I can more or less understand what it tries to imply. From here, we see some parameters. Okay, don't have to worry about all. We see temperature here. There's a constant here. Z is height. D is the damping or depth, the deepness. Z is actually height. This is damping depth. It's a constant. And then we have the kappa value, and then omega is the period. This omega is the one, this oscillation here. So one thing to note here is that slow variation penetrates deeper in terms of flux. So if the variation is very large, it might be hot and cold very fast, but then the amount that the ground can absorb is less. But if they say the variation is slower, there's more time for the ground to absorb more. That can be implied from this equation here, and I think from the trend here. Okay, so you could try. You have this equation. You could try a few values. You could change the Z. You can change the D. You calculate by hand. So this K and all that. So even K is given, and so on. And then you can look at how it varies using that equation. It's just plug. And then the values itself, you just play around. Let's say the temperature here, you start at 30 degrees or maybe 20 degrees, and then you just see how it varies. But here we see some of the trend. So overland, this is the summary of it. Overland, vertical cross-section sketch of net radiative input to the surface flux, F, and resulting heat fluxes into the air and ground for different scenarios. So daytime, A, nighttime, daytime over dry, desert, and this one is oasis effect during daytime. So during the daytime, net radiation. So this blue color is for evaporation, a lot larger than sensible heat. And then the ground absorbs the energy. This is during the daytime. More evaporation, less, some sensible heat release, but then less than evaporation. And the ground also absorbs. For nighttime, we have long wave radiation out, and then sensible heat going downwards. That means the ground absorbs. Latent heat, some of them condenses. The water vapor in the air condenses. When it condenses, it goes to the ground. But then the heat from the ground is released at night. This is for daytime, but over dry desert. Notice that sensible heat is a lot higher than latent heat, and the ground absorbs. This is the oasis effect. Okay, during the daytime, with hot, dry wind blowing over a moist, vegetated surface. So because it's dry, The air above here is dry, so of course latent heat will be large. But sensible heat actually goes down because dry heat. Here the temperature is quite high, then it goes in. But here, because it's very dry, there's a lot of evaporation. And then still some from the ground. This is from the sun. So the last slide, over land. You've seen this already. I think I don't have to talk that much. So again, we have the net radiation without the global radiation. This is the latent heat. This is sensible heat. This is the ground flux. Notice the change. At night, the ground flux is small but positive. During the day, it's negative but larger. Then becomes negative again. And it becomes positive again at night. Latent heat, if it's at the equator, yeah, it'd be large here. Then if it's sensible, usually the latent heat is a lot larger than the sensible heat, but that one depends on the surface. Most of the time it's this way. In Malaysia and so on, definitely this latent heat is a lot larger than the sensible heat in Malaysia.